Hey, I hope everybody's doing well. In this video, I want to talk about a concept called implicit differentiation. This is a use of the chain rule. So let me remind you what the chain rule is. The chain rule involves the composition of functions. I have an inside and an outside function. The way I normally say this is when I want to take a derivative of an inside-outside combination, I take the derivative of the outside and I leave the inside alone. And then I multiply this by the derivative of the inside. Well, implicit differentiation really is, I consider, just a change in notation. So here's an example. Suppose I have a function, and we're going to call it y. And I know this function is a variable, or in the variable of x. So a lot of times we will see equations that are written like this. But I want to remember that y is actually a function. We can consider it a variable as well, but I want to think of it as a function. So this is the way I like to first initiate this notation here. So if y is equal to g of x, then I am looking at the equation g of x squared is equal to 3x plus 1. Now I look on the left-hand side. If I want to take a derivative of this, the inside function is g and the outside function is the squaring. So if I take a derivative of this entire equation, d dx, the derivative with respect to x, I wind up getting take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. So I'm basically just doing this, where f is the squaring function. I have an equal sign in this. I'm taking derivative of an entire equation. So what I do to one side, I do to the other. Derivative of 3x, well, that gets me 3. And this is using the chain rule. But if I wanted to rewrite this without this g of x in there, this is the way I would go about taking the derivative. The derivative of y squared, well, I want to think of y as the inside function and the squaring is the outside function. So I'm going to take the derivative of the outside, I'm going to leave the inside alone to the first power, and then multiply by the derivative of the inside. And the right-hand side is still 3. The end game of all this, or the initial question, should be solve for y prime. That's my actual question. So I could take this one step further, and I can solve for y prime. This is an algebra step at this point. Y prime is equal to 3 divided by 2y. And this column right here, that's an example of an implicit differentiation. So let's try another problem here. I'm going to get a little more complicated on you. Suppose I have an equation. X squared, y squared are involved. This is the equation of a circle of radius 3 centered at the origin. My question for you is determine y prime. More specifically, if I want to be very precise about this, I'm going to use the other definition, or the other notation, I should say, of the derivative with respect to x. The derivative of 9 is zeros, so that's going to be an easy one. Derivative of y squared. Listen to what I'm going to say here. I'm going to take the derivative of the outside, I'm going to leave the inside alone. I think you've heard me say that before. And then I want to multiply this by the derivative of the inside. Instead of using the y prime notation, I'm going to use dy over dx. Plus, I'm using the sum rule here. What's the derivative of x squared? Well, take the derivative of the outside, leave the inside alone. Derivative of x, well, that's the inside, x, right? Is dx over dx is equal to the derivative of 9. Now, most of the time, I don't even bother writing this, because I know this, well, that's just equal to 1. So prior to all this chain rule stuff and all this implicit differentiation stuff, if I asked you, what is the derivative of x squared? You would tell me 2x. Well, it still is 2x. There's nothing different about it. So I still have to do the algebra on this problem. I want to solve for dy dx. So 2y dy dx is equal to negative 2x. I'm subtracting 2x from both sides here. And then I'm going to divide by 2y. And I'm going to do a little cancellation at the same time. And this is an implicit differentiation problem. Remember what the derivative could stand for. It measures the slope of the tangent line. So if you think about coordinates or x and y value pairs that sit on this circle of radius 3, this particular formula here determines the slope of that tangent line. So here's a small example of an implicit differentiation problem. I hope you found that useful. If you have any questions, let me know. Have a great day. Bye.